Welcome to Brain Vision.
The first step of this problem is to figure out how fast the end of the arm is moving. And so if the arm has a radius of r and it swings through an angle theta, then the distance traveled is equal to r times theta, as long as theta is in radians here. And so we're told that theta is equal to 45 degrees. If you multiply this by pi and divide by 180, you get that 45 degrees is equal to 0.78 radians. Now, we're told that r is 0.7 meters. And so this yields that s is 0.546 meters when it goes through an angle of 45 degrees. And we're told that it does that in half a second. So that means that our velocity is double this per second, 1.092 meters per second. That's how fast the end of the arm is moving. And so if we want the radial acceleration, which I believe is what A is asking for, we need the velocity squared over radius. And so we can plug that in, we can plug radius in, and we get 1.7 meters per second squared. Now, part B, it wants a force diagram, but I was kind of confused on what they exactly wanted here. So, okay, Ben's glitching out. So if this is my drop of blood, I assume that they wanted something like a force pointing upward and a force pointing downward. The downward force is equal to the gravity, so it's m times g, where m is the mass of the blood droplet. And upward, we just have the centripetal force. So it's due to the radial acceleration, which is keeping it stationary there. And so I think that's what they want for part B. But the wording on this question is kind of confusing. So I'm just giving you my interpretation of the solution, what I understood it to be asking me. Now we need to figure out what the total force is and what direction it points in. And so we have to figure out what the total acceleration overcome is by the blood droplet. And so if there's gravity pulling it down by 9.8, and we have to apply an additional 1.7 meters per second squared to keep it rotating just in a circle, then the total acceleration overcome is the sum of the two. And so our total acceleration overcome is equal to 11.5 meters per second squared. And so the total force that we have to apply is equal to mass times the total acceleration. The mass of the blood droplet is 0.001 kilograms. And so we multiply that by 11.5, we get 0.0115 newtons. And this force, of course, points up because it needs to keep gravity from pulling the blood droplet down. Now, part D asks if the arm is not swinging, what is the required force? In this case, we don't have two components of the acceleration. In this case, we just have our total acceleration is 9.8. It's just due to gravity. There's not that additional swinging motion we have to take into consideration. And so F total, just going to do the same thing here, multiply it by 0.001, and we get 0.0098 newtons. And so your blood vessels need to exert a larger force whenever your arms are not swinging, which makes intuitive sense. And the force is still pointed up here. So force point up here, and force is also pointed